Okay. Hi, everyone. I've been working with Aaron for the last 1 or 2 years, somewhere around there. So I thought I would do the introduction. So Aaron and I have been working on my favorite objects, the cold brown dwarfs. Aaron started, well, he finished his PhD in 2015, working where he did an all-sky map of interstellar dust using WISE, the WISE mid-infrared mission. And from there, he went on to reprocess all, hundreds and hundreds of terabytes of WISE, WISE data. And he pushed the sensitivity limits down by another magnitude or so, and he doubled the number of known white dwarfs. So that's brown dwarfs colder than 500 Kelvin. So he's a hero in my book. When you go from 20 to 40 of these things, it's huge, and he continues to push the limits of large databases, looking for faint things, moving things, bringing in citizen science people, search for Planet 9, implementing all sorts of clever stuff, looking to pull out the moving things so you don't have to, if you stack 10 years worth of survey data and you've got something moving, you tend to miss them because they're smeared out. So you have to be clever about pulling out and then stacking them and take account of the bullshit. So he's going to talk to us today about some of the most recent findings as he continues to plunge the depths of these large data. So over to you, Aaron.
Okay, yeah, thanks a lot, Sandy. And yeah, it's been really great to work with you over the past couple of years. And I really appreciate you pulling me in and helping me see the light as far as how much of what should have been an obvious synergy to me with Gemini in my research program. So now I'm kind of hooked and I just have too many ideas for Gemini proposals I want to write. But it's really been great collaborating with you so far on this stuff. So yeah, my main collaborators on this work are Sandy. Dan Castleton is a citizen scientist who happens to have discovered many of the main objects I'm going to focus on today. And then other collaborators include Sarah Logston, who's also here at NORLab in Tucson. So yeah, I'm Aaron Meisner. I'm a staff astronomer at NORLab based in Tucson. I work in the Community Science and Data Center, or CSDC for short. And today I'll be telling you about my work exploring the extremes, a new population of old and cold brown dwarfs. I think this title was essentially also from Sandy as well, so thanks to her for that. And yeah, the stuff I'm going to talk about is extremely well aligned with what Sandy had in the very nice intro there. So I'll start with a little bit of just a big picture view of why is it that we would be interested in studying cold brown dwarfs. Some of us just find this very interesting and we can't stop thinking about it, but maybe there are other people who work on, say, planets or stars who might not appreciate the different reasons why we study something that's kind of intermediate between planets and stars, but there are multiple different main reasons that are often cited. So one is that there's simply lots of brown dwarfs. If we want to understand our immediate galactic neighborhood around the sun, we definitely need to understand the substellar population. And so roughly speaking, there's one brown dwarf per 6 main sequence stars, as you can see in this figure at the right, which I really like. It's from one of Davy Kirkpatrick's papers where he did a census within 8 parsecs of the sun of everything, including white dwarfs, main sequence stars, and brown dwarfs. And he has this nice little diagram that kind of tries to be proportional to mass of stacking each object as a circle. By now, we've found a lot more objects, particularly the cold brown dwarfs. So this is in the process of being updated as we speak by Davy. Another reason that's very commonly cited is not necessarily for the purpose of brown dwarfs themselves, but because they can be useful as analogs to exoplanet atmospheres, but they have the key advantage that when you're looking at a brown dwarf, you're not interfered with by the glare of a bright primary star. And so the coldest brown dwarfs and giant exoplanets do overlap in temperature, and they can also overlap in mass. So some brown dwarfs can be of what we call planetary mass. That can either happen if you're just super cold and of a normal field age as a brown dwarf, or it could happen if you're moderately cold but very young, and so you're still in the process of cooling down. There's also other reasons some of my collaborators are very interested in these. So the mass function and initial mass function bridging between the lowest mass red dwarf stars and largest giant planets. So we want to know how efficient star and planet formation are in this kind of intermediate range. And we also can learn more about the process of star formation at low mass. For example, the multiplicity function as a function of masses and separation. And also things like whether the star formation efficiency at low masses might depend on other variables like metallicity in addition to just mass. And so this plot at the right also shows you the temperature ranges by which we define the brown dwarfs, most of which are L, T, or Y dwarfs. And you can see the temperature ranges there, but Y dwarfs, which I'll focus on more so than the others in this talk, are the coldest, and the boundary isn't perfectly defined, but roughly speaking, Y dwarfs have temperatures of below 450 or below roughly 500 Kelvin. And for reference, Jupiter is kind of in the 150 Kelvin ballpark. So it's not quite as cold as Jupiter. So those are all the reasons why in a proposal, I might say that I was interested in getting telescope time to look at brown dwarfs. But kind of, to be honest, when I wake up every day and I'm excited to search for brown dwarfs and study them, it's kind of a different set of reasons that motivates me. And I would characterize that more as being like just a curiosity about sort of what's out there in the immediate neighborhood of the sun, because it's possible that we don't really know. For example, there could be even Jupiter or Saturn-sized companion to the sun in the very distant solar system, and that might not have been detectable to any of our prior searches. So what I really like to do is to mine and process huge archival data sets and look for sort of the rarest of the rare. And in the cases of brown dwarfs, this list is kind of what I assemble, and I think about what are the really interesting things that I love to pull out among the billions of stars and galaxies and the tens of trillions of pixels of WISE data. So this is actually a list that I made from the Stewart Symposium here in Arizona in 2018. And I'm kind of disappointed and frustrated to say that we've discovered almost none of these things in the time since. We were hoping certainly to have discovered a brown dwarf colder than the current record holder, WISE 0855, which is at 250 Kelvin, but we haven't, which is surprising in some ways because we've gone so much deeper with our searches. And then some of these other ones get a little more speculative towards the bottom, right? Like say a Planet X scenario at the bottom, like maybe that exists, but it's quite possible we haven't detected it just simply because it doesn't exist. Another example of that is that there could well be a substellar neighbor that's very cold, that's closer to the sun than Proxima Centauri. So these are the types of things I think about when I'm building new data products or doing ambitious new data analyses, is kind of like, how could we find these ultra rare but potentially really impactful discoveries? The one thing that we have succeeded at is the very top one. As Sandy mentioned, we've roughly doubled the sample of known white dwarfs, which is nice. And I'll talk some more about that later on in this presentation. So yeah, this leaves me with, as I said, some frustration and some questions. So why haven't we discovered any Jupiter temperature brown dwarfs? Like, there's no reason in my mind why they shouldn't be out there. And we're so much more sensitive than prior searches in the infrared. It just seems like we should have found them by now, but we haven't. And then also, what have we discovered in the meantime while we were looking for these extremely cold brown dwarfs? And so there's a few thoughts that we have about this, and several of them relate to this topic that I'm going to focus on for the rest of the talk about old and cold brown dwarfs. And so because brown dwarfs cool over billions of years as they age, there's this thought that maybe we need to understand the oldest brown dwarfs in order to know how to properly search for the coldest brown dwarf. So maybe we've just been doing our searches entirely wrong and we've been misguided. And so, that depends in detail on the mass function at early times. Where was the universe forming very low mass brown dwarfs at early epochs? We don't really know that, but we also just generally don't know much at all about very old and cold brown dwarfs. So with this Gemini work that Sandy and I have been doing, we've really been trying to start down this path of getting a better understanding of old and cold brown dwarfs to answer this question. Another possibility, which is kind of shown by the picture at the bottom here, is maybe the coldest brown dwarfs are very diverse, just like we know giant exoplanets are diverse, and just like we know the giant planets in our own solar system are diverse. And again, maybe this is hampering our searches because we keep looking for things. We want them to look like WISE 0855, the coldest brown dwarf. But maybe once you get down to those cold planet-like temperatures, maybe it's just kind of a zoo of all different properties. And we shouldn't be making such strict, for example, color selections as we've been doing. And one challenge here is that our options as far as discovery of Jupiter temperature brown dwarfs at present are pretty limited. So WISE, which I'll talk much more about in this talk, is a NASA infrared satellite. WISE is really good for doing a full sky search at reasonable depth. And a more recent development here is that JWST, perhaps just by staring at the near vicinity of some of the coldest Y dwarfs, perhaps there could be an even colder object sitting right next to it and sort of like a resolved multiple there. So historically speaking, that's kind of the way that colder and colder classes of brown dwarfs have been found. So I wouldn't be surprised if JWST comes in here and kind of flips the chessboard on us. But really WISE and JWST are the main ones that come to mind as being plausible right now. And Sandy had a very nice Astro 2020 white paper that covers the sort of importance of trying to discover the coldest brown dwarfs or free-floating giant planets near the sun, but also the fact that this is really, really challenging to do. So in this talk, I'm going to focus on using WISE as a discovery engine for finding the oldest and coldest brown dwarfs, and then also using Gemini Observatory in particular as a sort of crucial follow-up step for the candidates that we identify in WISE. So yeah, I just wanted to give a little bit of an overview of WISE. I spend a lot of time thinking about it, but maybe not everyone else does. It stands for Wide Field Infrared Survey Explorer. It's a 40 centimeter telescope, so it's small, but it's powerful because it's in space. It has a pretty wide field of view in accord with its name, about a degree by a degree. It makes one full sky mapping every 6 months, during which it's operational. And another critical thing to think about when you're analyzing WISE data is that compared to, say, Gemini or ground-based optical imaging, it has much poorer angular resolution of 6 arc seconds to 12 arc seconds. So that really influences how you go about analyzing data, because you basically have pervasive blending even outside of the galactic plane. So the bands of WISE go from W1 to W4, from blue to red, and they go from about 3.4 microns at W1 to 22 microns at W4. In this talk, I'm really going to focus specifically on the 2 bluer bands, because those are the most relevant for identifying cold brown dwarfs, which have their emission peaking near W2 in this 4 to 5 micron range. So as Sandy mentioned, I've spent a lot of my time in practice, not so much following up brown dwarfs, but trying to make data products and tools that enable the discovery of more brown dwarfs in archival data sets. And so I'm going to give a little bit of background about exactly how I've been doing that. The idea is that I've been repurposing this big NEO-WISE mission, which is an extension to the original WISE mission, which has been going on now for about 9 years. So this is a kind of infographic that I like to show illustrating the WISE timeline. So it launched in late 2009. It completed its first sky pass in the first half of 2010 in all 4 of its bands. It eventually lost cryogen, and so it's only been continuing from mid-2010 onward in its 2 bluest bands, W1 and W2, which is actually fine for brown dwarfs because those are the most sensitive and relevant. And as you can see, it continues operating to this day. Actually, next week, NEO-WISE is going to release another year of data, another 35 terabytes of images that I'm going to start downloading. So that's exciting. But when I think about analyzing the NEO-WISE data set, I think about the fact that it's good for more than just asteroids, which is nominally what it's funded for. And when you're studying asteroids, all you really need is the single exposure images. But if you want to do something like extragalactic astrophysics or galactic astrophysics with brown dwarfs or low mass stars, you probably want co-added data products. And so for many years, the default co-added data product that you've had from the WISE mission itself was called AllWISE. And kind of ironically now, AllWISE is only like 1/10 of the WISE data. So at least in the 2 bluest bands. And so there's a lot more we can do if we're willing to go back to the single exposures and make our own custom co-added data of WISE over the entire sky. And so that's what I've been doing. For example, you can get 9 or 10 times greater exposure time than AllWISE by stacking these together in a static sky fashion, which, as you might imagine, it's good for detecting faint galaxies. In the time domain, which is maybe a little more relevant for brown dwarfs because we're looking for them move over time across the sky, the time baseline that we have now is more than 20 times longer than AllWISE. And so this really opens up a huge parameter space for various science cases, including brown dwarf discovery via proper motions, and also other things like studying quasar variability in the mid-infrared over long timescales, which hasn't been that well studied so far. So what's the catch? As Sandy alluded to, there's something like 45 million single exposures that make up all this data now, each of which is kind of a megapixel in size. And so that's about 315 terabytes of data. So for the purposes of this talk, I'm going to skip over all the gory details of how I do this data processing. But suffice it to say that you can't just wake up one day and do this on your laptop. You need real high performance computing resources, which I've been able to get access through the Department of Energy and the DESI legacy imaging surveys, which use some of my data products to select targets for DESI. So I'll just, as I said, I'll skip all the painful details of trying to process all this data and just go to the fun results. So one thing that you can do is simply stack all the data together and go much deeper. So I hope this is showing an image blink here, where you can see the noise is greatly reduced by having 9 years of data versus 1 year of data, which is not surprising. We brand our data products with this unwise label. If you don't like that, it was invented by Dustin Lang, so you can blame him instead of me. And so we call these the full depth unwise coads because we just stack them in such a way that it's optimized for detecting very faint galaxies that don't move. And you go more than twice as deep by having all this extra data. Now, personally, I like working with images a lot, but I know that most astronomers like catalogs. And so fittingly, we have something called the unwise catalog that builds off of the full depth unwise coads. And we use something that's called the crowdsource software, which is a crowded field point source photometry catalog making software written by Eddie Schlafly, who's at STSci. And it just does a really great job of deblending and modeling the sources. So what you're seeing on the top here is a blink between the unwise catalog model and the data, and WISE is in space, so we can make really exquisite PSF models, including things like the diffraction spikes way far out. And you can just see that it's almost impossible to tell the difference between the data and the model. So crowdsource does a really good job of deblending, which is critical, as we'll see later, for finding some of the coldest brown dwarfs, because often as these cold brown dwarfs move across the sky, they'll cross over some background object that has a normal color, which will totally throw off our searches if we aren't aggressively deblending and deblending correctly. This is just a plot to show that indeed at the catalog level, looking at the cosmos region is kind of a truth area, that indeed we go twice as deep. I won't focus too much on the exact numbers here. I think this is my only slide where I digress into extragalactic astronomy, but you might ask, what does it matter to go twice as deep? The answer is it does matter a lot. You get a lot more volume for brown dwarfs, but also for passive galaxies, you get a very favorable K correction. And so by going twice as deep, you get twice as many galaxies at redshift 0 to 1, 3 times more galaxies at redshifts 1 to 2, and 6 times more galaxies at Z greater than 2. And so this is publicly available. There's more than 500 million galaxies over the whole sky and more than 2 billion unique sources as well. Okay, so that was kind of the static sky part of this talk. I wanted to mention some of the time resolved, as we call it, unwise data products. So these are the time resolved unwise coads. And so if you think about how fast a brown dwarf moves across the sky, it's not actually moving all that quickly. And when WISE makes each of its twice yearly sky passes, each sky pass only lasts about a day or so. So during that day, a given brown dwarf isn't going to move appreciably relative to the large WISE PSF. And so if you stack on a per sky pass basis, you can go 1.3 or more magnitudes deeper at each epoch while also cleaning out various different artifacts. So in this case, I've labeled an asteroid as an artifact, even though probably not everyone would do so. And then you can also see a satellite as another example. So on the left is a single exposure, and on the right is what you get by making these epochal unwise coads, as I call them. And this allows you to do deeper motion and variability searches than you could with just the single exposures, and cleaner as well. So building on both the unwise catalog and the time resolved unwise coads, we built this thing called CatWise 2020, led by Peter Eisenhart and Fed in Morocco at JPL and IPAC. And the idea here is that unwise catalog provides the detection step. So it provides your list of sources, so 2 billion sources. And then you run the all-wise photometry pipeline, which has this neat aspect where it's called motion aware. So it not only fits fluxes, but it also fits a linear proper motion to every single source. So you get 2 billion mid-infrared proper motions, much better than ever before, because you're essentially leveraging that you have much more WISE plus neo-WISE data than you had for all WISE in a much longer time baseline. So the bottom plot just shows that any way you slice this, you're getting a huge gain. So at fixed magnitude towards the faint end, you're doing 10 times better in terms of the proper motion uncertainties, or equivalently at a fixed proper motion uncertainty, you're going 3 mags deeper. So again, this is just opening up a really big parameter space for discovering more cold brown dwarfs, which is the ultimate goal, at least for me. So the most recent time domain data product that I've made with all of this WISE data is what I called untimely. Again, this was Dustin Lang's idea. So I wasn't smart enough to think of this name myself, but I kind of like it. And the idea here is that it's an unwise catalog for every WISE sky pass. So if you were to think about the problem of discovering cold brown dwarfs as analogous to the problem of linking asteroid tracklets, this is how you would do it. You would have these deep co-added epochal detections, which are shown at the right here. There's this example of a fast-moving 900 Kelvin brown dwarf, and it indeed shows up as kind of a linear tracklet and untimely. I won't go into much detail here other than to say I set the detection thresholds really low because I wanted to find very faint and fast-moving brown dwarfs. This is effectively like having 32 all-sky unwise catalogs because you have 2 bands times 16 sky passes. There's about 45 billion total detections in this catalog, and it took about 225,000 CPU hours to generate it. It was run at NERSC Cori, which is a DOE supercomputer. I should also say that the image blink, hopefully you're seeing an image blink playing on the left there with a brown dwarf that's moving towards the bottom right over time. So this is something we call the WiseView image blinker. And it was actually built by a citizen scientist named Dan Castledon, who comes from the tech industry, at least for his day job. And this is a publicly available tool, but it's one of those things where, like, you know, once I saw it, I couldn't live without it because it's just such a nice way of taking this huge multi-terabyte data set and just looking at it in your browser and being able to adjust the stretch and the contrast and all that seamlessly. It's useful certainly for other applications as well, like variability, I found. So yeah, to conclude the part of this about data products that have enabled more brown dwarf discoveries, these are the list of things we've made. So it's the deepest ever 3 to 5 micron full sky maps, which we call the full depth unwise coads. There's this new class of all sky time domain maps at 3 to 5 microns, which we call time resolved unwise coads. There's the deepest full sky catalog at the same wavelength range, which is the unwise catalog. The deepest full sky mid-infrared proper motions, which are CatWise 2020. And then the deepest all sky mid-infrared tracklets and light curves, which is the most recent one, untimely. And all of these, I'm happy to say all of these have been made public, so it's not like we're trying to hide any of this or keep it to ourselves. We like the idea of making things that are useful because we realize that these are probably useful for other things than just what we want to do with them, in my case, brown dwarfs. Yeah, so a last part here on the methodology. This isn't exactly data products, but I did want to mention a little bit about the methodology of how we've been going about making some of our best discoveries. And one of the strategies that we've employed is going into the realm of citizen science. And so there was this citizen science project called Backyard Worlds. The full name is formally Backyard Worlds: Planet 9 that I co-founded in 2017. And the idea is to crowdsource the visual search for cold brown dwarfs. So the way that we look for brown dwarfs is that, as you might have seen in that previous WiseView blink, they have this distinctive look when you blink them in the time resolved unwise coads. They look kind of orange, which has to do with the fact that they're brighter in W2 than in W1 as compared to normal colored sources, like main sequence stars or normal galaxies. And then they're also moving. So the idea is to look for faint red things that move, basically. And this is a task that can be done by PhD researchers, and we do it, but it can also be done by other folks who are just enthusiastic about science and astronomy. So we launched the citizen science project Backyard Worlds in February 2017, which kind of disturbingly is 6 years ago. This is on Zooniverse. It's been funded by NASA through ADAP and NSF through, I think it's AAG, over the years. Our volunteers look at unwise time series blinks, namely the time resolved unwise coads that we've uploaded to Zooniverse. We've had over 8 million classifications so far, where classification is like the unit of work. in this universe. So it's kind of like one person looking at one blink of a 10 arc minute by 10 arc minute patch of the sky. And if you think about it, this is equivalent to staring at the entire sky about 6 times over, which is great because we want to look everywhere to uncover the most unusual and rare brown dwarfs. We have more than 77,000 registered users by now. Participants from all 50 US states, Washington, DC, Puerto Rico, and 167 countries. It's not actually all that straightforward to estimate how many unique users we have because you're allowed to participate without registering. But we think that number is about 200,000 unique volunteer contributors, which is kind of similar to the ratio of registered to unregistered across the universe. And then another fun stat that I like is that we've discovered about 4,000 motion confirmed LTY dwarfs to date, just by staring at these deep and clean time resolved analyzed coads. And if you do a small amount of math, that turns out to be about 1.75 discoveries on average per day. So it's, at the time when we launched this, I wasn't sure how successful or popular or not this would be, but it's really been a lot of fun, and it's really been scientifically productive as well. And a lot of the stuff that the volunteer participants have discovered, there's no way I would have discovered that myself. So yeah, I really have appreciated being a part of this citizen science methodology. A little more on the citizen science human element part. Basically, our volunteers come from a pretty broad range of backgrounds, both geographically and also in terms of what they do for a day job. So this ranges from pulmonology to the tech industry to, we definitely have like high school students and other students who sometimes sign on to our telecons on their lunch break, which is kind of fun. But anyway, it's a big effort, and I think it's really valuable to have different perspectives and different people looking at the data with different training and tool sets, because it just helps us to find everything and make sure we haven't missed anything unusual or special anywhere on the sky. I also just wanted to put in a brief plug here for this new project called Backyard World's Cool Neighbors, of which I am the PI. It's a NORLab-led and NASA-funded spinoff of the original Backyard Worlds project. It's launching on Zooniverse soon. And the project was actually built by 2 of my NORLab interns last summer, Noah Shapira and Austin Humphreys, who were really, really talented and productive. It was a lot of fun working with them. Our logo is shown on the right. And one of the main differences relative to Backyard Worlds is just that Cool Neighbors uses machine learning to pre-select extreme brown dwarfs, where by extreme, I mean cold and or old. And that's a pretty stark contrast compared to Backyard Worlds Planet 9, which just shows random sky patches. So we think this is going to be a lot better and help us to hone in on the specific populations that we're most interested in, like these old and cold brown dwarfs. Okay, I think that's all I had for the methodology part. So now I'm going to go to the results of what we found and what we've done with Gemini. So as Sandy alluded to at the start, we've done a lot of work towards filling in the Y dwarf census. In most cases, we don't really know how old these are necessarily, but these are definitely cold. So on the left, you see a histogram of, in gray, the previously known Y dwarfs before we started this whole Catwise and Backyard Worlds business. There were about 25 of them. And now with the red additions that come from Catwise and Backyard Worlds, which are based on Unwise as far as what the image input actually is, we've essentially gone up to a little more than 50. And so what you see is kind of exactly what you might expect, that we're filling in the faint part of the population. We're just going deeper in the same data. On the right, you see what's called a reduced proper motion diagram. So reduced proper motion is kind of like a proxy for luminosity in the event that you don't have full trigonometric parallax information for these objects, which we generally don't. And so a higher reduced proper motion is an indication potentially of lower luminosity. And you can see that WISE-0855, this kind of remarkable 250 Kelvin brown dwarf, is almost all alone in the bottom right of the plot. But our discoveries with Catwise and Backyard Worlds are sort of starting to bridge this gap. And we'd hoped to, extend even beyond WISE-0855, but we haven't done that yet. I would also note that I use the term identified Y dwarfs here because we know based on their colors and their parallaxes, at least we think that they must be Y dwarfs, but there's different ways you could define a known Y dwarf, including needing spectroscopy. And so spectroscopy of these has been really challenging because they're just so incredibly faint. And we've started actually getting the very first spectroscopic confirmations of these very faint backyard worlds and catwise discovered wide dwarfs through a JWST Cycle 1 program. So that's been really neat. Yeah, as I mentioned before, we've roughly doubled the sample depending on how you count the fact that we don't generally have spectroscopy of all of these. So now I want to shift focus really to the topic of old and cold brown dwarfs, which, looking back, it wasn't what we set out to study by any means. And so it kind of took us by surprise as being this really interesting science case for the types of data products we were building and the types of proper motion searches that we were doing. So here's a color plot that I made for my 2020 paper. It was about a Spitzer program that I was the PI of, where we had selected some very faint and fast moving brown dwarfs. And the hope was that we would discover a bunch of wide dwarfs, which are very red in Spitzer channel 1 minus channel 2 color, which is the x-axis. So that means they would be on the right of this plot. And they're also very red in terms of the J minus channel 2 color. And that would mean that the wide dwarfs would be on the upper right part of this plot. So you see that 1446 object is an example of a wide dwarf we did indeed discover like we were trying to. Channel 1 is kind of like the Spitzer counterpart of Y's W1. So it's the 3 to 4 micron band. And then channel 2 is kind of the counterpart of Y's W2. So it's like the 4 to 5 micron band. And so when we did this big proper motion search in catwise, and when we wrote the proposal, we thought we were hoping to find a lot of objects in the upper right, because those would be new candidates, say, for a coldest known brown dwarf, or they would just be filling in the wide dwarf sample more broadly. But actually, what's turned out to be more interesting is in this dotted black area on the left with the big black arrow that says old and cold. And so I'll get to, in a few slides, why we think these are old and cold objects. But I have to admit that when I made this plot, it was basically just because Davey told me my paper needed at least one color diagram in it. And we had so little information on these objects that this is the only one you could really make that would be at all useful. So it was really just an afterthought, and we didn't appreciate at the time how interesting these objects would be that are near the yellow pentagon. So the yellow pentagon is a benchmark brown dwarf that has a known metallicity from its higher mass primary of, I believe, minus 0.75 dex. And what you can see is that several of our very fast moving discoveries that have high reduced proper motion, so potentially low luminosity and or high kinematics, those are the green diamonds. Those also cluster right around this benchmark old and cold brown dwarf with a low metallicity. And so this was definitely the first hint that there was something interesting going on with these very faint and fast moving objects, that they may be an old and cold population distinct from the rest of the brown dwarf sequence that you can kind of see in the dashed purple here. So in the end, it's turned out that the upper left part of this plot has turned out to be more interesting than the upper right, even though that's not how we set out to do it. So the other thing that kind of made this whole story about old and cold brown dwarfs gel together for the first time was something like 6 months to a year after that plot that I just showed was published. Adam Schneider, who I work with on Backyard Worlds, published what he referred to as potentially the first 2 extreme T-type subdwarfs. So that's kind of a mouthful and a weird term. We use the shorthand ESDTs for this. So in low mass stars and substellar objects in this field, subdwarf has the meaning of being a metallicity of roughly minus 0.5 dex. ESD, or extreme subdwarf, means metallicity of roughly minus 1 dex, and then USD, or ultra subdwarf, means metallicity of roughly minus 1.5 dex, so kind of halo-like. So just to try to get rid of the confusion of the jargon here, but in more practical terms, what we're labeling ESDTs are temperatures below 1400 Kelvin, so in the T-dwarf or lower range in terms of temperature, and then also a metallicity that we think is less than or equal to minus 1. So that's where the E comes from for extreme, because that's sort of the metallicity bracket that it would fall under. So on the left, you can see that Adam found, through a mixture of searches, including Backyard Worlds, these 2 objects, Y's 1810 and Y's 04014, that have really bizarre spectra as compared to any other standards. They basically don't fit any standards that we know of. And what's also interesting is that independently, he kind of made the same color plot, which is shown on the right as what I had just shown in the previous slide. And interestingly enough, these two objects with really weird spectra that suggest they're cold T dwarfs, but with very low metallicity, they live in the same color outlier space as what we had selected with Spitzer sort of by accident, but not known what they were. The other thing about this is that this is a pretty new area to be trying to go to objects this cold and this low metallicity. So the models are actually an area of very active development. And in addition to not matching the standards of other known objects that have spectra, these extreme T-type subdwarf candidates also don't match very well with any models. And so Sandy and I, for example, have been working with Pascal Chamberlain and Mark Phillips on developing further models here to see if we can learn more about what's going on with these objects and also just have a better suite of models in general for brown dwarfs and exoplanets. Yeah, and then the thing that really cemented this idea that we were looking at a new population of old and cold brown dwarfs was when we made this plot. So this plot is from my 2021 paper, which shows that as you go to lower metallicity in a new grid of models made for us by Mike Line at ASU, you get these different tracks in temperature, and the tracks start moving up and to the left in such a way that they move exactly into this color selection box where we had seen our candidate, very old and cold and low metallicity brown dwarfs. And so I think once we saw this, we really thought, okay, we're onto something. We have kind of this nominal selection box that we've drawn here. We can really focus on the idea of exploring what it means for these to be old and cold brown dwarfs. And we can also try to go back into our survey archives and specifically select for these unusual color outlier properties, given that we see it empirically and we also see it in the models. So yeah, in the rest of the talk, I'm going to talk about what we've been finding in this old and cold brown dwarf regime and the Gemini follow-up we've been doing of them. So one of the most interesting discoveries that we've made, which was actually published in one of my 2020 papers, but we didn't realize how unusual it was at the time, is called WISE 1534. Also known as the accident. So that is a technical term from the literature. It was published in Davies' 2021 paper as such. So I don't feel too bad about using it. It was discovered accidentally by a backyard world citizen scientist. Once again, the one and only Dan Castleton. And it lives in a quadrant all its own as compared to the rest of the entire 20 parsec LTY brown dwarf census. So on the left, you're seeing a color diagram. And it's something like a 7 mag outlier there at fixed Spitzer color. And then again, it's something like an 8 mag outlier in the color versus absolute mag plot, where you have, again, at fixed Spitzer color, and you're doing this in terms of J absolute mag. And you can see on the right, that's actually kind of representative of the discovery image that we had in this case, because Dan thought he was looking at a candidate in the center of this blink, but it just so happened that in the corner of the blink, there was something else going on, which turns out to be this really interesting object. And just in case you think that this is really subtle and questionable as far as, is this noise or an actual object, it gets even more dicey from here. So I have some examples of that I think will be fun to look at. But one thing we are pretty confident about with the accident is that it's a halo brown dwarf. And the reason is because we've detected it not only in WISE, but also in Spitzer and multiple epochs plus HST as well. And we get a nice parallax plus proper motion fit at 16 parsecs. Its tangential velocity is more than 200 kilometers per second, which is quite high. And basically for any reasonable radial velocity value you might choose for this object, it's in the halo according to our tomb ray diagram. One other notable thing about this is that only 2 of this new old and cold ESDT population has parallaxes, the accident and WISE 1810, which turned out to be surprisingly near it, within 10 parsecs, actually. That was a paper by Nicolas Ledoux. And so it's been pretty unusual to see that these objects are turning up to be a factor of many closer than we think they are, which maybe is hinting that this is a very pervasive and vast population that's just been previously overlooked because they're so faint. Okay, so now now on to the Gemini follow-up. So Sandy very kindly had an approved, I believe, 2022A Gemini program that I was a co-I on. And in particular, this Gemini program targeted the accident for very deep J-band imaging follow-up. What you see on the left is about a 20 arc second by 20 arc second field of view in the Gemini J image. Kind of annoyingly, the object happens to be almost right on top of two galaxies. So what I did was I went and I modeled the two galaxies as 2D Gaussians to try to subtract them. And hopefully you can see in that image link there, once you subtract, you're left with a kind of like maybe 5 sigma source. And that is the accident WISE 1543. It falls within about 1 pixel or better of where we expected it to be in the Gemini image. So we definitely have the right counterpart. But it's just amazingly faint in the near infrared, which really just goes to show how important and crucial it is to have Gemini for this type of work. Its J magnitude is 24.5 Vega. So I think we use something like 6.5 hours of on-source time to get this detection. It's the first ever ground-based detection of this object. All the other prior detections were from WISE, Spitzer, and HST. So yeah, just delving deeper into this Gemini program in 2022A led by Sandy. All of the black points now on this updated color plot, it's basically the same one I've been showing this whole time of W1 minus W2 and J minus W2. All of the black points on here come from our Gemini follow-up. So we had a mixture of both Gemini North and Gemini South in here. And Sandy very generously orchestrated all of this as far as like making sure all the observations were done correctly and making sure that the images were all reduced. So I really, really appreciate all of her work on this. It's been great to collaborate with her on this. And basically what you can see here is that now with this new Gemini follow-up, we're starting to maybe see a sequence here that's runs sort of not parallel, but kind of parallel to these two other dotted line sequences, which are at higher metallicity. So again, you can see that as you move to lower metallicity, you start getting the sequence compressing itself towards the upper left. And so I think with this Gemini follow-up, we're starting to maybe see hints of the sequence for these even more extreme old and cold brown dwarfs. But it still needs more work. It's just kind of painstaking to get this necessary deep near infrared follow-up for such faint and red objects. Yeah, so going back to the accident a little bit more, we want to know, for example, what are its temperature and metallicity, because we have such limited information. This Gemini J data point is super valuable for that. And so if you look at the plot at the bottom right, there's a series of dashed gray lines, which are isotemperature lines between the gray line, which is 0 metallicity, solar metallicity, and the green line, which is a metallicity of -1, I believe. And so the accident falls somewhere in this subsolar metallicity range with a temperature of about 400 Kelvin, according to this diagnostic. Depending on other color diagnostics, you can get a temperature as high as 550 Kelvin though. So even with our Gemini follow-up of this object, we still can't really conclusively say whether it is or is not the first Y-type subdwarf if we're assuming that Y is roughly equivalent to a temperature less than 450 Kelvin, which maybe isn't a great assumption because we may not properly understand how the T-Y boundary works as a function of metallicity. That's something we could hopefully learn from this object more about. But yeah, this is a great plot made by Sandy, and it gives us some further insight that perhaps this object is as cold as 400 Kelvin, which would make it one of the very coldest known brown dwarfs. In keeping with the theme that basically every observation we ever take of the accident looks weirder than we expected, we again have the situation with our Gemini J band magnitude. So what we can do, because of the fact that we have this Hubble magnitude and this wide F110 filter, we can look at the F110 minus J color, which is telling you something about how the spectrum is behaving in the 0.9 to 1.4 micron range. And yeah, the accident is weird and unprecedented in this color as well. There's this interesting kind of linear trend that you see that for most other Y dwarfs, they're getting bluer and bluer in this color as you go to colder temperatures, so later spectral types. That's what you see on the left. And then the accident is just in a totally different ballpark here, being much bluer, although with big error bars due to the blending that we had to deal with. So anyway, this is really hinting at maybe something is unusual about the near infrared spectrum as well with the accident. And indeed, we see this in the models that Pascal has made in the past, where the very wide filter in the black is F110W and J is around 1.25 microns. And so as you go to lower metallicity, the blue is low metallicity, the red is solar, you get this dramatic shifting of the peaks such that you get a much less in the J band peak relative to the peak in the sort of Y band area. And that could be hinting at an alignment between our suspicion that this is a very low metallicity object and what we see in this color outlier aspect of its Gemini data. Here's another really great plot that Sandy contributed from, again, her follow-up program in 2022A at Gemini. The great thing about this is you can pretty much just read off the conclusions, which are that Y minus J in the top, it doesn't really appear to separate old and cold objects all that well from the bulk of brown dwarfs, except perhaps at the very coldest temperatures where we kind of lack data right now. J minus H excess appears to be a relatively consistent and robust indicator of low metallicity. So it might be good to, in the future, get more H band from Gemini. And then J minus K is perhaps a mixed bag. It's not clear whether there's consistently a J minus K excess for this old and cold sample. So in the very last part of this talk, I just wanted to focus on, as I said, we're going to look at some even more dicey candidates than what we've looked at before. We're pushing as far as we possibly can with this WISE data because we just don't have anything else to work with right now. And the NEO Surveyor is the WISE successor, but that's still probably like 5 years away. So does anybody see a brown dwarf in this image blink at the right? I like these ones where you could tell me there's a brown dwarf and I still wouldn't find it. If it's a helpful hint, the brown dwarf is right in the middle. So if you look at this with difference imaging, do you see anything now? There's a, right in the center, there's a, I don't know if you can see my mouse, but there's this object that's moving towards the upper left over time. And this is in a very crowded field, but coincidentally, it has past Spitzer coverage. And so that establishes a very deep limit on its Spitzer 3 to 4 micron flux. And yeah, in detail, oops, didn't want to do that. In detail, if you look at the Spitzer limit implied, it's second only in how red it is in Spitzer to WISE 0855. So we're definitely interested in Gemini follow-up of this object, but it may be challenging because it's in such a dense field. We need to think more about how exactly we're going to manage that. But that could be a new candidate for the coldest brown dwarf. And it's amusing that it's basically hidden right in front of a much brighter background source. And I'm just amazed that Dan discovered that because you could have told me there was a brown dwarf in that field and I never would have found it. Here's another one very recently discovered by Dan. Again, I will pose to you the question of, can you find a brown dwarf in this picture? And I don't think I could, but Dan has very conveniently nicknamed this the on purpose to contrast with the accident because he discovered this in a dedicated deep machine learning search to try to find more objects like the accident. And so here's what happens if you put a harder stretch on it, difference imaging, and you smooth by the PSF. Do you see something in the middle now moving towards the upper left over time? I don't know if you can see my mouse. So this is all very consistent with what Sandy said about we're just pushing the data to the absolute limit now. And we did in fact get Gemini follow-up of this one. We have a possible counterpart, but again, it's blended with a galaxy. So we probably need another epoch here. But I just wanted to mention that I had never proposed for fast turnaround before as PI, I don't believe, and it was a really positive experience. Like, it wasn't bad at all to review the other proposals, and our data came in early and with better conditions than we asked for. It was all just super smooth, and it was great to have such a fast turnaround on, you know, not only the review, but also getting the data. We likely need another epoch to confirm the motion, though, to make sure we have the right counterpart. And then the nice thing about the on purpose, if we have the right counterpart in Gemini, which maybe we don't, but it kind of completes the sequence here of objects in this old and cold brown dwarf population. So it bridges right in the middle between what we think are these extreme T-type subdwarfs and the accident, which is just kind of all off on its own. So we think that with Gemini now, perhaps we're starting to make some real progress towards a robust sequence of very old and cold brown dwarfs, but it needs more work. So yeah, my last slide is just to say some of these next steps that come to mind. Of course, like everyone else, we'd very much like to get JWST spectroscopy of some of this sample, but the odds may be long here, so we can't count on any of that. As I mentioned, NEO Surveyor is the successor to WISE. It's very similar to WISE, but it'll just be deeper because it has a wider field of view. So all of the data analysis challenges with like blending and so forth that WISE has will just be amplified and similar in NEO Surveyor, and it's not for 5 years or so. We probably want to keep doing more Gemini imaging, perhaps more H and K to fill in those different colors. Gemini spectroscopy of the sample that we've gotten Gemini photometry for would be great to again, work on these low temperature, low metallicity models. The calendar 2022 NEOWISE data is coming out next week, so I'll be busy processing that. Also, I've had really great experiences collaborating within NORLab with folks at Gemini, especially Sandy and CE. So I'm very interested in forming other collaborations with Gemini NORLab staff if there are opportunities to overlap with this type of work, even if it's using the WISE data for something other than brown dwarfs. And lastly, I'm always interested in making more different unwise data products. So if there's a wide range of things I could do, but if there's any feedback about what would be most useful or most relevant, I'd certainly be interested to hear that in my emails at the bottom. So thank you.
Questions?
What was the comment in the chat? Just, I love brown dwarfs.
And it's easy to find brown dwarf if they are in the center. Easier.
I have a question. This is Tom Jabal at my house, not at NORLab, not at Gemini, I mean.
Mm-hmm. Hi, yeah, sure.
This is a wonderful talk, Aaron. Just great work by amateurs and by professionals. It's terrific. My question is, you didn't say anything about the masses of these objects, and rightly so, I guess, because you know so little about them. But my guess would be that they must be fairly massive brown dwarfs. Otherwise, if they're that old, they would have cooled down to the point where they'd be even harder to detect.
Yeah. That intuition is exactly right. It's a little disappointing. This is the reason that it's become so trendy to look for young brown dwarfs, right? Because if you have a young brown dwarf that's a late L or early T, you have a good chance of that being a planetary mass object, which of course gets a lot of attention in the press and captivates people's imagination in various ways. But for the old brown dwarfs, you have exactly the opposite. So at a fixed temperature, you're actually looking at relatively massive objects. So one challenge with the masses is that some of the evolutionary grids don't actually go past 10 gigayears. So that's for starters. I think I did just for fun. I never published this, which maybe I should have, but just for fun, I looked at what is the mass of the accident if it has a 10 gigayear age and a temperature of 500 Kelvin, which maybe is a little underestimate for the age. And I think it came out to I believe the mean was a little under 30 Jupiter masses. So it's, you're not going to impress anybody with how planetary mass you are with these objects unless we go even way colder.
I only got a quick look at your spectra, your infrared spectra. It was surprising, and I guess due to the low metallicity that there's so little, if any, CO and methane in the near infrared. Did I miss something, or is there really almost no sign of them?
I'm not sure about CO, but we do think that the methane is driving a lot of what we see. The reduction of the amount of methane is driving a lot of what we see in the trends of color with metallicity. So yeah, in this plot, my basic intuition for what's happening here is that as you go to low metallicity, you're moving left on this plot because you're getting less methane absorption in the sort of 3 to 4 micron range, which is boosting your W1 relative to W2, giving you a bluer color there. And then you're also getting increased H2 collision-induced absorption opacity in the near infrared. And so that's making you redder along the y-axis. So that's pushing you upwards. Off the top of my head, I don't really know exactly how CO would play in here. Maybe Sandy could comment more on that. or it can be a topic to discuss with Sandy at some other time.
I haven't thought about the CO. That would be mostly at 5 microns a ton. What struck me in the spectra, the synthetic spectra, but you can really see the H2, which just smushing everything at 1 micron. So we've got cold enough and high enough pressure now. Before I just thought of H2 as the K band, but now we're seeing the 2 microns. But now we're seeing the 1 micron.
Yeah.
Can you show the spectra, Aaron? Maybe
Yeah.
the synthetic spectra, I was thinking. Pascal's models.
Oh, okay, sorry, yeah. Gotcha. This?
Yeah. See that broad absorption at 1.1, 1.2.
Mm-hmm.
That's the H2.
I see. It's not, yeah, it's not water.
No, it's H2 kicking in. It's already smushed all the 2 micron flux out, and now it's
Yeah.
it's smushing the 1 micron flux. So there's so little flux, and then these things are so faint.
Mm-hmm. Amazing.
Yeah.
Michael, you want to unmute and speak up?
Oh, hi, Aaron. Great talk. Hey, I wanted to circle back to this comment you made at the beginning, how this sense of disappointment that nothing cooler than 0855 has been found. I was wondering, there are all these new generations of models now, at least for the solar metallicity population. I was wondering if you had taken a look at how many more things you actually do expect to find by going deeper, because of course, as you go down a little bit in mass, generally things get much, much fainter. So how much extra headroom, so to speak, or floor room,
Yeah,
you thought about this?
Thanks, Mike. That's a really good question. Thanks for attending the talk. I'm not sure I expected to see you here, but yeah, it's great that you were here to attend. So yeah, I mean, the true answer is that's a great idea, and I haven't looked into it as much as probably I should. There have been simple estimates. For example, Ned Wright had a paper where he just tried to totally scale off of the W2 magnitude and the W2 depth of 0855 and how much deeper we're going. And he found something like an expectation of, I think it was like 14 to 35 WISE 0855 analogs should be found, but there was, with what he called the statistics of 1, there was quite a huge range. So actually, one of my opinions about this, which is kind of less exciting maybe, is just that it may not actually be that big of a statistical fluke in terms of number of sigma to only have 1 WISE 0855 or colder object. Some of the people I work with don't like to hear that, but if you look at it in terms of like the number of sigma, it's not many sigma of an outlier. It could use more work though, as you say.
Is there any last question? If not, we reach the top of the hour. So let's thank Aaron again. See you next time.
Thanks, Aaron. See you.